Hello, everyone. My name is Lizzie Buchanan. I'm a graduate student at Dartmouth College working with Vladimir Chernov. I hope to meet many of you at the upcoming synchronous events. So first, a big thank you to all of the organizers for setting up everything for this conference, and especially thank you to Samantha Allen for inviting me to speak at this topic group. Okay, so what am I speaking about today? I am talking about the Jones polynomial of a fibered positive link. So I'm going to begin at the end with a statement of our main result. And that is that for a fibered positive knot, we must have that the maximum degree of the Jones polynomial has to be less than or equal to 4 times the minimum degree of the Jones polynomial. So why would people care about that? Well, I mean, obviously, if you're interested in fibered knots, this could be helpful. If you're interested in positive knots, and also for those of you who are interested in braid positive knots, because braid positive knots are actually a subclass of fibered positive knots. So I'm just going to draw a picture of that briefly. So we have fibered knots, positive knots, fibered positive knots, and braid positive knots. And I do want to note that not every fibered positive knot is a braid positive knot. There are knots that do not fall into that classification. So one way that we could use this theorem is to exclude certain knots from having a braid positive representation, because certainly if they aren't fibered and positive, then they can't be braid positive. This theorem is also helpful if you are like me and you're interested in being able to distinguish almost positive knots from positive knots. So in general, it is very hard to distinguish those two groups. There are many invariants that apply to positive knots, but for which you have the same conclusion for almost positive knots. So for example, the signature being negative, or certain statements about the coefficient of the lowest degree term in the Jones polynomial. A lot of these criteria that we could use to determine if something is positive or to exclude a knot from being positive can't rule out almost positive knots. However, this theorem does do that in some cases. There do exist almost positive knots for which we don't have that the maximum degree exponent is less than or equal to 4 times the minimum degree. So in those cases, we are able to quite quickly exclude the possibility of a knot having a positive diagram. And therefore, we are able to sometimes show that a given knot is almost positive, which again, in general, is very hard to do. So yeah, as I said, proving that knots aren't positive is pretty difficult. And up until this year, we actually had not even completed the positivity classification of knots even up through crossing number 12. There were 7 12 crossing knots for which positivity remains unknown. But what's really fun is that the theorem that I mentioned actually can be applied to those 7 knots, and we are able to make conclusions about whether or not they are positive. So here are the remaining 12 crossing knots positive. Well, I've written down the Jones polynomials for those 7 knots. And we already know that these knots are fibered. So if they were positive, then they would be fibered positive knots, and then our theorem would apply. And so we can quickly check to see that these are not positive, because if they were, we would have to have that the maximum degree 13 for all of them would have to be less than or equal to 4 times the minimum degree. But here, 4 times the minimum degree would be 12, and 13 is not less than 12. So we are able to quickly check that these are not positive. So that means that earlier this year, we completed the classification of positivity of knots up through crossing 12. And that classification was also completed independently at around the same time by Alexander Storminov. So his method did not use this theorem at all. He used a computer-aided method. And actually, his method also showed knot positivity up through crossing number 15. So certainly it's surpassing 12 crossing knots. So the current state of it now is that we do know whether or not a given knot is positive up through crossing number 15. Okay, so now I want to talk a little bit about the world of the proof that goes into the proof of our main result here. So to do that, I'm going to begin going over a couple of known definitions having to do with knot diagrams and positive knot diagrams in particular. And then I'm going to talk about the new kinds of diagrams that we invented in order to prove our theorem. So the world of the proof. Okay, let's start with smoothings. So I'm going to be calling the smoothings A smoothings and B smoothings. They're shown in that diagram at the top. This might look familiar to you. It also is known as the 0 smoothings and 1 smoothings, or 0 resolutions and 1 resolutions, or A resolutions and B resolutions. These are all talking about the same thing. And so what we can do is we could take a knot diagram, so looking at then the far left on the picture on the bottom, and then if we performed A smoothings at every single crossing, we would then end up with a collection of circles, and that's shown in the middle picture there. And since we got those circles by performing A smoothings, we're going to call those A circles. And then similarly, if we had performed B smoothings everywhere, well, we're going to call that B circles. So that's shown in the picture on the bottom. And in particular, I also chose to use a positive link diagram because for the rest of the talk, we're going to be focusing on positive links. So then what we can do is focusing in on A smoothings. So we can look at then the A state graph. So what that means is I then draw a graph where I have a vertex that corresponds to every A circle that I got in the diagram. And then I'm going to draw an edge between vertices every time there was a crossing shared by those corresponding A circles. And for this picture, we see, for example, that there are 2 crossings shared by the dark pink circle and the navy circle. So then I will have 2 edges in my A state graph. And then the reduced A state graph is just going to be, I took the A state graph, but I removed duplicate edges. So in this example, since every pair of vertices was connected by 2 crossings, my reduced A state graph is just going to have 1 crossing between every vertex. Okay. So then we also want to note, this is a result from Alexander Stominov, that a positive link is going to be fibered if and only if it has a positive diagram for which the corresponding reduced A state graph is a tree. So an example was shown on the previous page. So here, this was actually an example of a fibered positive link because we ended up with this reduced A state graph as a tree. And you can read more about this in work from Alexander Stominov and also in work by Fuder, Calfagiani, and also Purcell, if you are interested. And so the theorem that we said at the beginning has to do with positive fibered knots and links. So the next couple of definitions are going to be essentially some very special kinds of diagrams of fibered positive links. So the first one we call a balanced diagram. So a balanced diagram is going to be a non-split positive link diagram in which every pair of circles either doesn't share any crossings or they share exactly 2 crossings. And also I want to have that the reduced A state graph is a tree. Putting that part in the definition that the reduced A state graph is a tree, again, that's going to mean that I'm actually talking about fibered knots and links in general. And then we're stating it this way because we're defining a diagram, not a knot or a link in general. So here, the example that we already showed was actually a good example of a balanced link diagram. And so we have this nice balance because every time that we do have vertices that are connected to each other, they're connected by exactly 2. So every pair that is connected by exactly the same number of edges. So there's a nice balance there. And what turns out to be really wonderful about balanced link diagrams is that there's actually an interesting relationship between the number of B circles in a balanced diagram and the number of link components. Namely, in a balanced diagram, the number of B circles is equal to the number of link components. So we have this balance, this equality between those two quantities. And I have drawn in a picture showing that on the example that we've used before. So here we have a link diagram, then drawn the A circles. Then the third picture shows the B circles. And then in the last, I've just colored in the link components. And as you can see, the number of B circles is equal to the number of link components. And what this does is this will allow us to use these different quantities interchangeably if we are looking at known inequalities about the maximum degree of the Jones polynomial. And so that's how we can really make use of this key theorem. We have this observation about balanced diagrams, and then we can apply that to the Jones polynomial for the corresponding knot. But of course, this is just for this specific kind of fibered positive link diagrams. We need to have that balance. We need the fact that for every pair of A circles, they either share exactly 2 crossings or they don't share any. However, we can then generalize this a little bit to define a burdened link diagram. So a burdened link diagram is essentially like a balanced diagram, but instead of being balanced, it is overburdened with extraneous edges. So by that, it means that we're going to have a positive diagram where the reduced A state graph is a tree. Again, that's going to give us that fiberedness property. And we're also going to require that every pair of A circles that share crossings, every pair of A circles that share crossings will have to share at least 2 crossings. So again, it's essentially a balanced diagram, but a burdened could be overburdened with extraneous edges. And then what we can do is we can take our key theorem, saying that for a balanced diagram, the number of B circles is equal to the number of link components. And if we weaken that statement a little bit, we can apply it to burdened diagrams. So what we'll get is a corollary that in a burdened diagram, the number of B circles is going to be less than or equal to 2m plus the number of link components. And this is where m is the number of extra crossings in the diagram. So really this is the number of crossings in the diagram, in the burdened diagram, that if you smooth them away, you would get a balanced link diagram. So here smoothing, if you smoothed according to the orientation. So for positive link, that's also equivalent to smoothing in the A smoothing. And again, this inequality can then later be inserted into known inequalities about the maximum degree of the Jones polynomial for positive links to end up giving us our theorem. So, but let's dive a little bit deeper, and I'm going to explain a little bit about some more concepts relating to these diagrams that are involved in proving this theorem about the balanced diagram, where there's a balance between the number of B circles and the number of link components. So the first one is the concept of matching pairs. So in a balanced diagram, by definition, adjacent A circles will share exactly 2 crossings, no more, no less. And so then I'm just going to go ahead and we'll call every such pair of crossings, we'll call them a matching pair. And this is a suggestive name because we're going to find that there is a match between the B circles and the link components. So, but here I've drawn, essentially, we can imagine we've zoomed in on a pair of crossings, and these are involved in A circles. So that's drawn in on the left with the dark pink and the blue. And the green boxes show the remaining parts of the diagram. So again, since the underlying reduced A state graph of this balanced diagram is a tree, we do know that then if we had smoothed these 2 crossings according to their orientation, we would actually disconnect the diagram. So we can actually draw the matching pair with the 1/2 of the rest of the diagram on the left in a green box and the remaining half of the diagram on the right in the other green box. And as shown here, when we smooth the matching pair according to its orientation, we disconnect the diagram And then we create two new smaller balance diagrams. So what's fun about that is that then we get the sense of, oh, we're splitting these into smaller things. So if we can start small, think tall, we are setting ourselves up to have a series of induction arguments. And that is what goes into the proof. We show things on these smaller diagrams, and then we can induct to show it to be true in general. So then now we're imagining we have matching pairs. And now we want to think about, okay, what could the B circles look like? If I took my diagram, if I took a diagram and I looked at the matching pairs, what would the B circles look like? On the matching pair, would those arcs be part of the same B circles? Would they be part of different ones? And so there are four options here drawn out. So first of all, either there can be one B circle that's involved in the arcs of the matching pair, or there could be two. And then there's multiple ways for each. And it turns out that there's quite a similar situation of what the possibilities could look like for how the link components are drawn in this diagram. And I also want to note that we're able to determine that there's only these four possibilities for the B circles, because we do have the constraint that a B circle can't cross itself. So there's no way that B smoothing could have happened where I came up here at the top and then connected down here on the right, because then at some point later, I would have had to cross from here to here. And then that would be impossible because B circles can't cross each other. So that's one restriction that led us to only having four possibilities. And now, of course, link components certainly can cross over one another. But here for the components, the added restriction is, well, certainly the components have to follow the orientation. So since we're drawing in, okay, here's our matching pair, it would be impossible for me to, for example, connect the link components up like this, because then I would be violating the pre-prescribed orientation of our link diagram. So I have these B circle possibilities and I have these component possibilities. And certainly from looking at these diagrams, they are almost exactly the same. And the colors are also suggestively hinting that there is a lot of similarity going on here. There's a lot of connection. And what ends up happening is that we want to look at, hey, when do these pictures actually correspond with each other? The top left picture looks almost identical to the bottom left. These pictures are almost identical. And also these ones on the far right, this top one and this bottom one, they look pretty similar. I mean, like the colors don't quite go, there's sort of a mixing and matching there, but they seem to go along, work in harmony with one another. So what we're going to do is we define a special kind of matching pairs. We call them synchronized pairs. So a matching pair is synchronized essentially if exactly those rows of pictures match up. So more precisely, if every pair of arcs that are part of the same A circle then are also part of the same B circle exactly when they're also part of the same link component. So that's what it means to be synchronized. But really what that means is the two rows of pictures on the previous slide exactly match up. So we would say that if you had B circles that looked like this, and your components looked like this, and they matched up, this is synchronized. It's a synchronized pair. Okay. So then what happens next is we can also describe a related definition, again, suggesting that these things are related. We would say that then a balanced link diagram is synchronized if not necessarily arcs that are involved in the same matching pair, but just any arcs that are involved in the same A circle anywhere in the diagram. If those arcs are part of the same B circle, if and only if they're part of the same link component. And if that was true for every selected pair of arcs on any given A circle, anywhere in the diagram, then we would say that that balanced diagram is synchronized. And so here is a picture of a balanced diagram that we've seen before. And also, if you look closely, you can see that this is synchronized. So if I look at this pair of arcs on the same A circle, so let's use a different color, red, this arc, these two arcs are both part of the gray A circle. And then if I look, well, they are part of different B circles, and they are a part of different link components. And if I had chosen any other pair of arcs that are part of the same A circle in this diagram, I would have seen the same thing. Either they would both be part of the same B circle and part of the same link components, or they would both be part of different B circles and different B components. And what ends up happening is that, like, as we can see in this example, also in particular, every matching pair is synchronized, and we can go back and forth with that. If every matching pair is synchronized, then the diagram is synchronized and vice versa. And so what that means is if we start to count things up, and there's a bit of induction arguments involved here that I'm sort of sweeping under the rug, but if we count these things up, we're always going to have the same number of B circles and the same number of link components. They're going to happen time and time again. And so that is what will end up giving us our theorem that we had before, namely that in a balanced diagram, the number of B circles is going to be equal to the number of link components. And as I said, we can sort of weaken that a little bit in order to generalize it to burden diagrams. And then what we're able to do is pause and say, okay, so what was it that we just said? Well, we can plug this into known results about the Jones polynomial, and then we can end up with the Jones polynomial of a burdened link diagram with n link components must satisfy that the maximum degree of the Jones polynomial has to be less than or equal to 4 times the minimum degree of the Jones polynomial plus number of link components plus 1/2. And so then in particular, if we were dealing with a burdened knot diagram, then that n minus 1 just turns into 0. And so we have a neater, cleaner statement there. But our favorite thing about the Jones polynomial, or one of our favorite things, is that it is a invariant. It's an invariant, so it is diagram independent. So this won't just apply to a particular burdened link diagram. It'll apply to any diagram of that link or that knot. And so then we also can pause and remember, okay, but the whole point of these burdened diagrams and these balanced diagrams was that actually under the rug, what we were saying is these were diagrams of a positive fibered link. And the restrictions that we had about essentially excluding crossings in the A-state graph that there was just one edge means that we don't have any nugatory crossings. So an equivalent definition of a burdened diagram is that it's a reduced positive diagram of a positive fibered link. So reduced meaning that there are no nugatory crossings, things that can just be undid just by going like this. So which means that actually we have a larger theorem, which is that the Jones polynomial of a fibered positive link with n link components must satisfy this inequality that we have here. And so in particular, the Jones polynomial of a fibered positive knot has to satisfy that the maximum degree, the Jones polynomial has to be less than or equal to 4 times the minimum degree. And so that is our main result. So thank you very much for listening. And as I said before, I look forward to meeting many of you in the upcoming days. Thank you so much. Oh, and please feel free to come to the office hours. I would really love to discuss this with anyone who has any questions. Thank you so much.